Okay, what's up, everyone? So today we were gonna discuss a mock test on triple integrals. This mock test is gonna contain several tips and tricks needed in the section on triple integrals. And the exercises we're gonna solve are gonna range over conversions between different coordinate systems, setting up triple integrals, and finding the boundaries for the regions, and then some evaluation tricks for triple integrals. So let's get started doing that. So let's begin with some conversions here. Recall the coordinate systems. So just as a quick warm-up, let's do these quickly. So recall these coordinate systems, cylindrical and spherical coordinates, and let's do these conversions real quick. So the part A here, we notice that this is just r squared equals 25. So in cylindrical, this is just r squared, which means this is r equals 5. And this finishes this one. So let's see this one. Um, so in this case, I'm doing cylindrical as well. So z is z, z doesn't change. And then x squared plus y squared is r squared. And hence this simplifies us to z equals 2r. So this finishes this one. So let's look at the third one. Since we see x squared plus y squared plus z squared, to simplify the shape of this surface, it makes sense to use spherical. And indeed, this is a sphere up to like a rearrangement of terms. But here we don't need to rearrange terms. We can just see that the sum of these three is rho squared based on spherical coordinates. And the right-hand side is just 8 times the z, which is rho cosine phi. And then for phi, for positive phi, non-zero, excuse me, for positive rho, we can cancel a rho, and this means that rho is just simply 8 cosine phi. So this is the final shape of the answer. Um, um, so let's do the last one before we move to something else. So in this case, in spherical, z is going to change and it's going to become rho cosine phi. And then we have a square root of 3, square root of, so x squared plus y squared in this case is r squared. Except that you should be careful that in spherical, the R means something different than in cylindrical. So cylindrical R is a variable, but here we have to rearrange things in terms of in cylindrical R is a variable of integration. Here we have to rewrite things in terms of phi rho and theta. This is square root of 3. And if you use the definition of x and y in spherical and you simplify, you will see that r must be of this shape. In other words, excuse me, here I'm missing an r. So r here, so square root of 3, and r is going to be rho sine phi. And then this could be simplified more. We see that we can cancel the rows. We can cancel some of those. And we end up with cosine phi equaling square root of 3 sine phi. And then tan phi, this means if you rearrange, this means tan phi is 1 over square root of 3. And thus you can find what phi is. And phi in this case is pi over 6. So you can rearrange to see that in this case phi is pi over 6 by taking arctan, for example. So this finishes the answer for this one. So these are some quick conversions between the three coordinate systems. Okay, and as a challenge for you, try to convert back. Try to take these answers that we arrived at and convert back, and you will see that the process is going to be just the you're going to reverse engineer what we've done here, and you will arrive at the Cartesian coordinate system. Excuse me, equations. Okay, so let's keep going. Let's discuss something else now. Maybe let's solve these quick warm-ups as well. How do we do conversions like that? Well, in this case, we just have to use the fact that x is rho cosine theta sine phi, y is rho sine theta sine phi. So let's put a phi here. And then z is going to be simply rho cosine phi. And then since you know rho, phi, and theta, you can find x, y, and z. And I'll leave it to you, but I'll give you the answer. It's going to be something like 3 square root of 6 over 2, 3 square root of 6 over 2, and then 3. So this finishes A2. So these are just some quick warm-up before we get to the real harder stuff, I guess. So let's look at this question. How do we rewrite this cone as a phi equals something? We've already seen in the previous part, we've seen that a cone like this can be converted. So this is a cone. It can be converted to spherical coordinates. Excuse me. It can be converted to something of the form phi equals constant in spherical coordinates by simply converting everything, every variable you see to the coordinate to the corresponding coordinate system. So in this particular case, what happens is that if you start in part A, so in part A, what happens is that if you replace everything by the corresponding spherical coordinate thing, so z is rho cosine phi, and then there's a square root of r squared here, which is just r, excuse me, just r. Um, and we know that r is just rho sine phi, which means if you cancel the rows, if you cancel the rows and divide by and do cross ratio, you will see that tan phi is 2, which means phi is arctan of 2. And this finishes part A. So this gives you the phi sub 0 or the phi naught. It's literally this thing. So this is the phi naught. And then for part B, you just have to observe that when we speak of spherical coordinates, we're making an angle, uh, especially when we're talking about a cone centered at 0, like this one. Um, so the thing you need to remember here is that the z-axis, the phi, excuse me, it's the angle we make with the z-axis. So the phi is the angle we make with the z-axis, and we have this cone, and we know that the opening of this cone, we know that the opening angle is given by phi naught over here. And hence, the inequality you need here is that phi is going to be ranging between this phi naught that we found and 0, or between 0 and that angle. And we're starting at 0 because at angle 0, we're already inside the region. Um, so this was a quick one as well. Okay, so let's get to the real stuff. Let's get into the harder stuff, I guess. So we're going to be setting up integrals. I'm not going to be evaluating things, but in some of the questions, I will be evaluating things because there are some tricks there, or at least I'll be giving the hint there, and you will do the evaluation. So let's begin with this one over here. So let's find the volume between bounded by the paraboloid and the plane z equals 0. So you can see that this is a paraboloid because if you plug a few z's, so for every z you plug, you're going to get a circle. And there's a particularly interesting z, which is z equals 9, at which you get x squared plus y squared equals 0, and that's going to be the top of the paraboloid. So in other words, let's sketch a quick figure here. So let's see how this looks. So it's going to be a paraboloid starting uh, at 9 and going all the way down, something like this. So let's not draw something from the bottom. So it's going to be a paraboloid like this. And the point here is that we'd like to set up the integral. It's up to you which coordinate system to use. I mean, here the question asks us to do it in coordinate system, in cylindrical coordinate system. And that's clear because if I look at the equations of defining the region, I see that I have x squared plus y squared, and I know that cylindrical is the 3D generalization of polar coordinates. So it makes sense to use cylindrical. Um, if I were to see something like x squared plus y squared plus z squared, I would have used spherical coordinates. But here, it makes sense to use cylindrical coordinates. So let's do that. So we gotta set up a triple integral, and then we're gonna begin with dz, and we're gonna apply polar coordinates on the xy plane. So RD theta. And let's see. So we're going to begin with the z simple. We're going to begin by setting up these thingies. So this is the z-axis. This is the x-axis. This is the y-axis. And again, you look at array parallel to the z-axis. So here maybe it's better to draw something like this just to see what's going on. So I'm entering at the bottom, which means the z equals 0 plane, the xy plane, and I'm going all the way up, and I'm exiting from the paraboloid, which means at z equals 9 minus x squared minus y squared. But this thing is just r squared, which means that this whole thing is just 9 minus r squared. Okay? And then we're integrating the function 1 because we're computing the volume of the region. So to be able to find the r and theta, we have to project things on the xy plane. But that's pretty clear here. It's basically a circle. But to see that, you have to intersect these two thingies, which means you have to put z equals 0 here. And you see that you have the circle x squared plus y squared equals to 9, which means r squared is 9, which means r is 3. Um, and thus, since we have a circle centered at 0, we're entering at r equals 0 and leaving at 3. And then the angle theta is free to go from 0 to 2 pi. So this finishes this question. As for the answer, it's going to be 81 pi, 81 pi over 2. But I'll leave the evaluation for you. If you attempt to do this in spherical coordinates, you will notice that you will have to use something related to solving a polynomial in degree 2 and using the quadratic formula. But I'll leave that for you as a challenge. Okay, so let's keep going. Let's discuss some more questions. So let's solve this question now. Let's find the volume between these two surfaces. And again, since I see x squared plus y squared plus z squared, it makes sense to, in order to simplify things, it makes sense to use spherical. In other words, since I see a sphere, it makes sense to use a spherical coordinate system. And we're gonna do that after we draw the region real quick. So let's draw the region. So the region here in this case, let's see how it looks. So we have the sphere. So let's sketch a quick figure here. So we got the cone and then we have the top sphere. So the cone is gonna be, it's gonna start at the origin, go all the way. You can plug in a few z's to see what it looks like. Um, but the point here is gonna this figure is gonna look like an ice cream of this shape. Um, this is the point 4, and the point where we um, we're gonna find the point of intersection between these two. But for now, let's see what we have. So this is the shape approximately, and then the integral. Let's see how it looks. So we're using spherical, so we gotta account for the change of variable factor, in other words, the Jacobian. So we have rho squared sine phi, d rho d phi d theta. And then we're gonna find what rho and phi are. So remember, rho is the 3D generalization of the R parameter that you used to use in polar. In other words, I'm gonna start at the origin and I'm gonna look at an arbitrary ray and see what happens to that ray. Um, in other words, I'm gonna be looking at a ray as a general ray here that starts at the origin and exits. So, in other words, we're starting with a distance 0 from the origin, and we're exiting at the sphere, but the sphere can be written as rho squared equals to 16, which means rho is 4. So we're exiting at rho equals 4. And since we're computing a volume, we're going to be integrating 1. And then let's see what happens to the other parameters. Basically, phi is the angle we make with the z-axis. However, at angle 0 with the z-axis, we're already inside the region. So we're gonna start at phi equals 0, and we're gonna go all the way to this line. But this line is totally determined by the cone. It has nothing to do with the sphere, and it's given by this equation. I believe we've probably have solved this in the previous question. So let me just show you again. So the conversion we did here, over here, we found that the corresponding angle is over here. It's phi equals to phi naught, and phi naught is arctan of 2. So this is the conversion to spherical coordinates. So if we go back here, in other words, this equation is phi equals to arctan of 2. And hence the angle here is going to be arctan of 2. Okay. And then how about theta? Well, theta is the angle we make with the with the x-axis. However, we see, for example, at the top here, we have a complete circle. In other words, we're covering every single angle between 0 and 2 pi, and hence the angle is going to be going between 0 and 2 pi for theta. Okay, so this finishes this question. And as for the answer, this is going to be something like 128 pi over 3 times 1 minus 1 over square root of 5. Okay, so this finishes this question. Um, um, and again, if you need more time to attempt the question or solve it, you can pause the video and then uh, and then see the answer that I'm doing here. Okay, so let's work on this one. This one introduces some important terminology, um, namely the density and the mass. So whenever we speak of a mass density function, a triple integral of that is going to be the so-called mass of the solid A. In other words, for every point in the region E, what you're doing is so for every point x, y, z inside here, you're assigning the mass z. So for every particle in E, you're assigning the mass based on the height. And then this integral is going to give you like the sum over these masses, and hence it's going to give you the overall mass of the solid E. Okay, so here the hint is to use cylindrical coordinates, but again, even if we didn't know that, this should be clear because we see x squared plus y squared. Hence, we think of polar, but a 3D generalization of that is cylindrical, and hence we're gonna use cylindrical coordinates. So let's draw the region real quick. We don't really have to here, but just as a good practice. This is X, this is Y, this is Z. And what's happening is it's a cylinder. Um, um, it's a cylinder because one of the variable is missing here, and we have a sum of squares. And moreover, the important part is that it's a cylinder oriented in the direction of the z-axis because the z is missing. So, in other words, um, it's going to be in the xy plane, it's going to be the circle of radius 3 centered at 0, 0, and you're going to go up, you're going to move that to get the 3D version. And we're going to stop at z equals 5. So this is 5. So the picture is something like this. Okay. So let's see how the triple integral will be. So the triple integral in this case, it's gonna be, let's see. So again, in spherical, in cylindrical, it's always worth trying a z simple first. In other words, beginning with dz and then applying polar on the xy plane. So dr d theta. And let's see where the z's range. So if we so here the inequalities do tell you where the z's range. So you can literally just blindly write this is 0, 5. But you could also visualize it like array parallel to the z-axis is going to enter at the xy plane and leave at the z equals 5 plane. So this is the first part. Um, um, Excuse me, this is r here. Dz, dr, d theta. So for r, we need the projection on the xy plane. However, we already have that. This is going to be it's the region bounded by the circle of center 0, 0, radius 3, which means in this case r squared equals 9 is the boundary, which means r equals 3 is the boundary. And again, in a circle centered at 0, 0, which is going to be this thing here, r is going to begin at 0 and it's going to leave at r equals 3. So this is 0 to 3. And then for theta, every angle is attainable because we have circles here. So it's 0 to pi. And as for delta, the z is going to stay z because in cylindrical we don't change z. And you can integrate this, and you should get the answer you should get is something like 225 over. So it's something like 225 pi, not something like it's exactly this number. Okay, so this gives you the mass in whatever unit. This gives you the mass of this solid E. Okay, let's keep going. Let's see what happens to this thing. So we'd like to evaluate this, or we'd like to set up the integral for this one. It's gonna be also an ice cream, perhaps with a different geometry. So 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 it's gonna look like this. So let's sketch this real quick. X, Y, Z. We got a paraboloid. If it's easier for you to see things in Cartesian, you may rewrite things in terms of X, Y, and Z instead of R theta Z. So here you're given the equations in cylindrical, but you can always convert things back to uh, Cartesian. And if you plug in a few z's, you will see that this is a cone and this is a paraboloid. So the paraboloid is gonna be the vertex of it is gonna be at 12 at z equals 12, and it's gonna go down. But you got the point. Something like this. Yeah. Again, it's an ice cream with a different geometry. Okay, so I guess since things are given to you in cylindrical coordinates, you don't need to think a lot. You don't need to think too much here. We're gonna use cylindrical, and it's gonna be r dz dr d theta. We're already given like the bounds for z, but again, you can see that since a ray parallel to the z-axis enters at z equals r and exits r 12 minus r squared, which is the paraboloid. And then we need to see what happens to the other bounds. This is a little bit tricky, but it's very doable. So let's look at this. We need the intersection between these two because that's going to give me the full projection on the XY plane. Remember, we're projecting on the XY plane, so we need to eliminate Z. You could set this equals to this. However, you will see that solving an equation for x and y here is hard. The alternative is to solve it in terms of r because that's easier. And even if you were given things in x and y, you should convert things to cylindrical and then solve because that makes things doable, I guess. So in this case, we're going to set r equals to 12 minus r squared. And if you solve this, um, solve this quadratic equation, it's going to be r plus 4 times r minus 3 equals 0. And then this means that r is 3 or r equals minus 4, but we ignore the minus 4 because r is always non-negative. It's positive. And other than that, this is simply a circle of radius 3, center 0, 0. So this is the projection is going to be a circle over here of radius 3 and center 0, 0. So r is going to be going from 0 to 3, and theta is going to be going from 0 to 2 pi. And you can see that the projection is this circle, this top of the cone over here. Okay, so this completes this question. Um, um, so yeah, this finishes this one. So we're gonna move to a second part of the test where we're gonna discuss some quick evaluations, and this is supposed to illustrate some symmetry and evaluation tricks. Um, I'm not gonna be doing the technical calculation things. These are things you guys can do. But I'm gonna show you just at least the harder part, how to do the harder part, and that's gonna be enough. Okay, so we got this integral, and we'd like to evaluate over the ball given by x squared plus y squared plus z squared less than or equal to 1. In other words, this is the sphere. Since it's a sphere, it makes sense to, since the boundary is a sphere, it makes sense to use spherical coordinates. And we're going to indeed use that. So the triple integral here is going to be in terms of spherical coordinates because x squared plus y squared plus z squared becomes simply rho squared. So the boundary is rho squared equals 1. And this thing has a rho squared here, and then the square root and the square cancel, and we have e to the minus rho, and then we have the Jacobian rho squared sine phi d rho d phi d theta. Okay, and yeah, that's pretty much it. Except that we have to set up the boundaries for this and spherical coordinates. And here's an important note for you. Whenever we're working with a sphere centered at 0, 0, 0, like the origin, it's gonna be always like um the full thing. So it's gonna be 0, 2 pi and 0 pi for phi. And for rho, it's gonna be 0, 1 in this case. But if you can't see it, excuse me, this should be pi. If you can't see it, of course, you can draw the region, and this is gonna be this is gonna quickly show you that if you have a sphere like this, then basically um, the if you start at the origin and look at a ray, that ray is starting at a distance 0, meaning rho equals 0, and exiting at the sphere, which is given in terms of this equation, which means rho equals 1. As of phi, it's the angle with the z-axis, so it's going to be going from 0 all the way to 2 pi, 2 pi. And then for theta, it's the angle with the x-axis, and of course with circles, with circular level curves, we're gonna go from 0 to 2 pi in this case. So this is quick. However, the important thing I wanna remark here is that when evaluating this, you can observe that I can integrate this thing with respect to rho separately, and I can take this out here and integrate it separately. But the important part is the thing I want to illustrate is that this integral over here, to evaluate it, you need to use integration by parts. To integrate this, you just need to remember how to do integration by parts. And what you can see here is that so I'm gonna do at least one of them, and then you do the second. So here you can put a minus, or you can put a derivative here, and you observe that you only need to pull a minus out, which puts it in the right form. And then we apply integration by parts to see that this is gonna be rho squared e to the minus rho between 0 and 1 minus the integral between 0 and 1, and now I differentiate this, so that's going to be 2 rho, so that's going to be 2 rho e to the minus rho d rho, and then I can repeat the process, namely I can put a derivative on this, and I see that this is going to be a plus now, because I added I multiplied by a minus, by a negative sign, and I can apply integration by parts on this one again. So this is going to be minus. So this one is going to evaluate to what? E to the minus 1. And then plus applying integration by parts again. So this is 2 rho e to the minus rho between 0 and 1, and then minus the integral between 0 and 1, and you differentiate this now, and it's at just simply at 2, and then e to the minus rho d rho. But hey, this is easy to integrate. It's simply, you can do a u sub, but you don't need to. This is easy to integrate. So when you finish this, you will end up with the answer 2 minus 5 over e. So this one is going to be 2 minus 5 over e. So let's move to this next. Okay, so let's move to this next question. So this illustrates the important terminology of an average value. So to average a function, what you need to do is you need to sum over the values of this. So if you're averaging a function over a region, what you need to do is you need to sum that function over that region and divide by the volume of the region. And summing in this case is going to be the triple integral for us over that region. So this is a sphere, of course. The boundaries of this is a sphere, so it makes sense to use spherical coordinates. However, the important part of this question is that I want to illustrate that you might have seen before that the volume of a ball of this form. So the volume of the ball, it has a closed form formula, which is 4 uh, pi r cubed over 3. And in this case, r is the radius and it's 2. So, I mean, it should have, if you're very picky, you would have wrote rho here instead of r, but this is an abuse of notation. But anyways, so r is 2. So if you compute this, this is 32 pi over 3. However, this formula, it's not like a magic formula. It really comes from a triple integral, remember, because a volume of a region can be really computed by integrating the function 1. And in this particular case, since we're integrating over a sphere, we're going to use spherical coordinates, d rho, d phi, d theta. And then, as I mentioned, when we're working over a sphere, the bounds are going to be easy to read. So rho is going to go from 0 to 2 because of this, and then phi is free from 0 to pi, and theta is free from 0 to 2 pi. So if you were to compute this integral, and this is an easy to compute integral, you would indeed get this number. There's another trick in this question that I want to illustrate. So maybe let me set up the integral again. So it's 0 to 2. Notice the region doesn't change here, so I'm integrating over the same region. So 0 to pi, and then 0 to 2 pi. And then we need to convert this thing to spherical coordinates, and then multiply by the Jacobian, or the change of variable factor. So x squared plus y squared is r squared. And remember that in spherical, r squared is rho squared sine squared phi. And then we got another term coming from the Jacobian, which is rho squared sine phi, d rho, d phi, d theta. And this is a square. And this is like a normal integral, like there's nothing new here, except that if you were to integrate this thing, you will have to compute an integral that you might think is hard, but it's not really hard. It's just something that you need to realize from trig identities. This integral is separable in the sense that you can integrate with respect to each variable separately. And if you carry out the integration, you will see that you will have to integrate the integral sine cubed phi d phi from 0 to pi, I believe. Yeah, from 0 to pi. You will have to integrate an integral of this form, and this it might seem scary, but it's really not. It really reminds you that whenever um, you can here decompose a sine, and then a sine squared is 1 minus cosine squared phi, and then you can use a u sub to find this. The point here is that a trig identity like sine squared plus cosine squared equals 1, um, it might be underestimated. I mean, you might underestimate the power of this. It's really powerful. So the point here is that integrals like this that might seem scary, they're really not if you use the simple stuff that you know. So if you use this decomposition, you will see that you will be integrating sine, which is easy to integrate, and then you will be integrating sine cosine squared. But for that, you can use a u sub like u equals cosine, and you can evaluate this thing. So this thing is going to be simply um, um, 4 over 3. So if you compute this as well, you will see that the value here is going to be um, I'm not sure if I have the value here. So I think um, I think I think it's going to be something like 256 pi over 15, but you can double check. I think this is the correct answer. Okay, so the important illustration here is that the volume that you might have formulas from from a different course, I guess. It's really an integral. You can compute it by a triple integral like this. And the second important thing is that a trig integral like this, it's computable. It's totally computable if you employ some tools that might seem like not so useful, but they are in fact very useful. Okay, so let's keep going. I want to illustrate. So this is a very important one, and it should take you like half a minute to solve it. But if you're not like used to the trick of symmetry, it might not seem very obvious to you. So I guess I'm gonna write down the answer to show you that this can be really written in half a minute, depending on how fast I am right now. But when I wrote the answer to this, it really took half a minute because symmetry is very powerful here. So let me write the answer and then I'm gonna justify. So the answer is, so this is 0 by symmetry. This finishes the question. And of course, so this is 0 by symmetry. And of course, if you were asked to justify here, and I'll need to take time to justify. So let me justify to you, I guess, at a slower pace what's going on. So let's consider the example, the function x dx between -1 and 1. If you carry out this integral, you will see that it's x squared over 2 between -1 and 1, and this is 0. What happened here is that we're integrating an odd function over a symmetric interval, over a symmetric region. So integrating an odd function as a general rule over a symmetric region, we're gonna get 0. So that's an important thing. However, this idea here is generalizable. It need not be in 1D. We can generalize it to multiple dimensions. Particularly, we can generalize it to 3D. And if we look here, we see that this function here is odd. It's odd in x. In the variable x, this function is odd. Moreover, the region is symmetric in x. What does that mean? So if you look at this region, if I replace x by minus x, if we call this region R, if I replace x by minus x, R doesn't change. So notice if I replace x here by minus x, the region doesn't change. And if you were to draw this, you will see that this is basically a cylinder cut by the two planes z equals 2 and z equals -2. And it is indeed symmetric about the x-axis, so it's going to look something like this. and it's indeed symmetric about with respect to the x variable. So integrating over a symmetric region with respect to the x variable, and we're integrating an odd function in the variable x. Hence, we must necessarily get the answer 0. So I hope that this actually has an important evaluation trick, and it can really save time. It can really save you time if you do it correctly. Just don't. Here's one thing. There's an important note here. Um, when I speak of symmetry, I mean it does apply in particular cases, but it doesn't mean that whatever integral you get, you're gonna just apply symmetry to it. That doesn't work like that. I mean, integrals do not necessarily you can't necessarily apply this to every integral just to be on the safe side. So just don't overdo it. I mean, sometimes it's easy to realize things, but just don't overdo it. This is what I'm saying, because you might go wrong in some cases. Okay, so I'm gonna keep going. I guess I'm gonna skip some of these because these are easily doable. I wanna work on this as a final question. So let's look at this question here. I want to just talk about an important trick here, and then or an important thing here, and then we're gonna wrap up this video. So the point here is that if you look at these two integrals, these are these give me the region and the region of integration in the xy plane because these are the xy variables. And what this is, this tells me that x is between 2 and -2, and y is between the square root of 4 minus x squared and minus that. So let me just, so 4 minus x squared. And the point here is that this is just a circle. This is just a circle of radius 2. And of course, if you don't believe me, just set y equal to that, square both sides, rearrange, and you see that this is a circle. And it's the full circle because we're saying that as we go parallel to the y-axis, we're entering at negative minus square root of 4 minus x squared and exiting at square root of 4 minus x squared. And our x is ranging all the way between -2 and 2. So this is the full circle. The important thing here is that um, this circle is moved in the z direction from 0 to 3, and hence what we obtain is a cylinder that starts at the z equals 0 plane and go all the way to the z equals 3 plane. So it's going to be a cylinder. It's going to be a cylinder like this. So like that. And this is 3. So it makes sense to use cylindrical coordinates. And of course, if we do that, so we can do that here. So let's see, dz r d theta. So maybe we need some space. So let me quickly rewrite things. So we need a little bit of space. Let's write rd dz d theta. Theta is going to range between 0 and 2 pi. So the way I'm telling is based on this figure. And then r is going from 0 to from 0 to 2. That's also because the radius is 2. So this is r equals 2. And then for z, we're entering here. So notice it doesn't change between Cartesian and cylindrical. So it's 0 to 3. But you can see it if you look at a ray parallel to the z-axis. We're entering at the z equals 0 plane and leaving at z equals 3. Okay, and then x squared plus y squared, this is just r squared. And if you look closely, you see that this is the answer. However, this is not the only answer. And the reason is that so if you recall, there's an important theorem that you must have learned in Calc 3, which is Fubini's theorem. And Fubini tells you if you're integrating over a rectangular region, you can interchange the order of integration without changing the value of the integral. In other words, you can integrate in whatever order of integration that you wish, of course, under some basic conditions. Particularly in this case, if you look closely, you see that D is also an answer because you can interchange these two integrals. So as long as all of the boundaries are constants, this is okay. So you can interchange these two integrals and these two variables. Um, so let me see what happened here. So it's right. So we interchanged these two variables, these over here, and the answer doesn't change. If this doesn't convince you, what you can do is you can observe. I mean, in this particular instance, you can see that, for example, this integrand is separable in the sense that you can integrate the R things and then the Z things and then the theta things separately. You can write this as a product of three integrals, and you can write this as a product of three integrals, and you see that these are one and the same. So, yeah, this is an important thing. Fubini. All right, this was the end of it. Thanks for watching.